Hi, I'm Eric Heim. I'm the principal investigator for this project. It's called A Series of Unlikely Events. In a nutshell, what we're trying to do is use models of machine learning to learn from sequential behaviors for the purposes of activities-based intelligence, but also modeling human expertise. And so I'll talk a little bit about what that means. This is the thing. So to talk about this a little bit, I'm going to use this example of monitoring these ships as they go about navigating this port, for instance. And so you can imagine if you're an intelligence analyst, you probably care about this because you want to know where these ships are doing, potentially doing anomalous things, potentially monitoring the behavior for what they're going to be doing. But really what I want to challenge everybody in the audience to do is, as I talk about this series of techniques that we're using, specifically a class of techniques called inverse reinforcement learning, to think about your problems in the context of what you guys are working on. So I'm going to talk about this as a driving example, but really think about what you guys have been working on and how it applies to your problems. So like I said, we're going to be modeling using inverse reinforcement learning these behaviors of ships. And so if we had a model of such behavior of these ships, what can we do? So if we are given a trajectory of a ship at a particular time, we can then simulate going forward, because if we have a model of what normal behavior is, we can then say, hey, in about like an hour, we expect the ship to be here, right? Similarly, if we see something deviate from that, we can say, hey, that was anomalous. Hey, the ship suddenly doubled back on itself. We had never seen a ship do that before. In our model, that says that's a really anomalous behavior, right? Similarly, if it exhibits some behavior and we can say things like, hey, the ship sort of avoided this area. Why did that happen? So an intelligence analyst could look at that and say, hey, what's going on in that location? Similarly, all these ships be going to this exact location. What's going on there? And finally, not just on the ship level, but on something like a larger scale with a lot of different ships. So if we have a lot of ships in this port, we can say, hey, over the first 3 months we were observing, they exhibited this type of behavior. Suddenly, they changed. What happened in that time period to make them change, right? And so all of this is with a model of the behaviors of these ships, okay? And so the goal of this work is we wanted to take this class of techniques called inverse reinforcement learning and then apply them to these such problems as the ship modeling scenario. And how do we do that for these DoD and intelligence community problems? So we've identified 3 particular issues with the current state of the art and the state of the practice. One of them is we need these techniques to scale to DoD problems. So as many of you know, in the DoD, there's tons of data. I've heard the saying, swimming in information, drowning in knowledge, or something, the other way around. But the point is there's a lot of data out there in these DoD operations. They collect it. We need to have our models scale to those DoD problems. Similarly, a lot of these methods, and I'll talk about this later, they tend not to be robust for rare events. And in a lot of DoD operations, what we care about are the rare events, right? We want to know, hey, how should we reason about these particular instances that we haven't seen before? And frankly, there's a lot of work to actually faithfully model problems in practice. So taking from the algorithms themselves, and then taking these DoD problems and taking them and modeling them as these problems. So the goal of this work is to create efficient, robust methods that faithfully model behaviors in these important operational domains. So with that as sort of the introduction, I'm going to talk about 3 different things. One, I'm going to give a very brief background on inverse reinforcement and what it is. Then I'm going to talk about some of the work we have done in terms of scaling these IRL methods to large-scale problems. And then I'm going to preview some of the directions that we have of upcoming work. Okay? So inverse reinforcement learning, in a nutshell, is simply taking some observed behaviors in the form of data and learning the preferences that led to those behaviors. So what do I mean? So if you take a look at, this may even have a pointer. Oh, nope. If you take a look at this box here, we can see the ship is in a certain state at a particular time, and it chooses to make an action. And what it does is it goes to a different state. So a particular trajectory of this ship is represented by a sequence of states and actions followed by another state and action, right? So it's transferring the ship from one state to another separated by actions. And if we have a lot of observations of this or data of this, what we can learn is this reward function R, which simply maps states and actions to some reward. And what reward should do is be high for states and actions we've observed quite frequently in the data and low for states and actions we have not. So what that means is, hey, this reward function expresses this idea of preference within our model, right? So if we've seen a particular behavior a lot, a ship being in a certain state and taking the same trajectory, that should be a high reward state in action. If we haven't seen it do that, that should be low reward. And if we have this model, we can play this forward to simulate the most high reward actions throughout time. Or, hey, we've seen this behavior. Were any of those behaviors low reward? And if that's the case, we can detect those as anomalies. So that's the particular formalisms we're using in this problem. Okay. So what are we doing in this? As I mentioned before, so if you look a lot of at sort of the research in this field, and there's actually a lot of inverse reinforcement learning that's being done even now. So if you look at the major publications in machine learning, there's new inverse reinforcement learning methods produced every time, right? So how do we take that stuff, as sort of Brenda discussed, from the recently possible to the mission practical? And the way we do this is through scaling through efficient implementation. So what we did is took a reference implementation from some of our collaborators, implemented it in Python, because it was in MATLAB. Python, if you're unfamiliar, is a programming language. And we applied different problems of different sizes and timed it. So in this first example, so in the first row here, the number of states an agent can be in is of 100, and the number of actions that they could take in each one of those states is 4. And the number of sequences or trajectories we've seen were 20 of them. The Python implementation to go from that data to a model that we could predict was something like 3 minutes. We then focused on a particular C++ implementation with, again, focusing on efficiency. We got that down to 5 seconds. And similarly, as we scale up problems to larger state spaces and action spaces, what we found is that we've scaled even better. So the punchline here is for a moderately sized problem that would take, again, a naive implementation, about a full day to train a model, we're now getting down to 3 minutes. So this is sort of a really good first step for us to be able to take these techniques and apply them to DoD scale problems. Okay? So what I'm going to show now, actually this is an older video, but I think it'll play. Yes. So I'm sort of playing around here a little bit with one of our demonstrations here. And unfortunately, I wasn't able to show our model as it attaches to this visualization, but it sort of gives you a scale for the type of problems we're considering. So this is New York Harbor. And these are a bunch of, this is data from the US Coast Guard as they track ships as they're going into New York Harbor. And so this is on the order of a couple million observations. And here's how our model sort of views these observations as they progress going forward. Now, what I'm not showing you is the model performing this, hey, prediction of where things are going. Unfortunately, I wasn't quite there with hooking up the model to this implementation. But going forward, I'm hoping to be able to post this online so you guys can, if you want to, go take a look at it and see what we're doing here. Okay? But this is a cool visualization tool we're working on. So I wanted to preview some of the upcoming directions we have. And so I sort of talked about this AIS shipping data, so AIS being the US Coast Guard data, as a particular example. But really, there's a lot of different, this formalism provides a lot of different potential applications. So what we're looking at here is potentially applying this to things like certain cyber systems. So if you're looking at network traffic over time, you can view each snapshot of that network traffic as being a state, and a transition to a new state or different network traffic as being an action to a new state. And if we have a model of this behavior over time, what we can do is say, hey, this system is behaving as we normally would expect, but if something happens that deviates from that normal policy or this normal reward structure, what we can say that is, hey, something's weird's going on this network. And you can imagine how this also applies to different cyber systems. Similarly, we can also take a look at this in the context of things like patterns of life. If we see soldier behaviors deviate from a normal behavior, we can then say, hey, we should probably pay attention to this. But that's sort of all of the same flavor. What I also want to point out is we have work in actually applying this to other domains other than sort of activity-based intelligence, where things like robotic control. So if you look at a lot of the literature now within inverse reinforcement learning, what we see is people are using this to do autonomous robotic controllers. And so what they're having is experts actually control robots, such as the one in the upper right-hand corner there, and to perform some task, and then taking those observations and then using that to train a model to be able to actually do autonomous driving, so to mimic that expert behavior of that robotic control. And extending that even further, what we're actually looking at now is to do that to actually teach novices how to perform tasks well. So imagine you have an intelligence analyst that is sitting there doing some task within his workflow, and he's an expert. He's doing it for years and years and years, and he's really efficient, and he does really great work. Imagine you have a new one coming in, you need to train him. Well, what would be potentially useful is a model of that expert's behavior such that when a novice gets to a certain point in that workflow, gets some recommendation based off of what the expert would have done in that situation. So maybe it guides them to a particular solution the expert would have gotten to. Maybe it's used for training. Maybe it's used for recommendations, right? Similarly, excuse me, we have used this work to actually adjust human behaviors as they go about their day-to-day lives. I'll talk a little bit of work. We have some academic collaborators to actually use like an app to suggest them proper actions to improve their health, okay? I'm actually going to skip this. Is there any way to click on this? Is it? Okay, that's good. I'll know that in a second. So with that human behaviors, we have two academic collaborators. One of them is now at the University of Washington, while the other one's at Carnegie Mellon. So Aninde, he did some awesome work in the human computer interaction side by using these methods in an app form to collect a bunch of data from students on campus about what their actions as they walk throughout campus, what they do at home, and what the activities they're doing. And they're having them record how much sleep they get each night, right? So you can imagine their activities throughout the day affects that. So given that data, what they're able to do is build a model such that they could say, hey, this action you took seemed to lead to less sleep. So for instance, they could suggest, hey, don't get that second coffee, and potentially you can sleep more. So this could be augmenting human behaviors based off of these models. Similarly, Stephanie Rosenthal, we just started working with her a couple months ago, but she just started this really awesome study which to model expert data scientists and how they behave relative to novices. So they had a bunch of expert data scientists and captured their workflow for a particular data science task and compared that to, and they had some metric to success. This was a classification task, so it's simply area under the ROC curve. So it's a very definite metric that shows that they did well on this task. And they had novices do the same task, and they performed worse according to this metric, and their workflows were very different. So what could be these methods could be potentially used for using that data is to build a model of expert behavior to then teach novices to perform better at that task. Again, the direct analogy here to a DoD operation could be something like teaching an analyst how to perform these tasks. And so the last thing I wanted to bring up is this robust behavior. And so I wonder if I can click on it. Will that work? Oh, well, awesome. So what we have here is we trained a method, a reinforcement learning method that uses the same formulas of inverse reinforcement learning on this robotic control task. And what we see here is we start the agent in this particular orientation, and we say, hey, we provide a reward structure to say run forward as fast as you possibly can. And using modern techniques, this is what's known as the proximal policy optimization technique. It does pretty well, right? This is sort of what you would expect. This is on par with some of the best reinforcement learning or learned agents for this task. Now, what happens here is if you just change the orientation of that agent's initial position just slightly from what you see on the top left to the top right, this is what happens. The agent fails miserably. So if you notice, it just sort of sits there and it doesn't know how to manipulate its limbs to perhaps achieve the performance that you would get here. And this is not just this particular orientation. You can adjust the orientation such and it fails miserably. Now, what does this mean for inverse reinforcement learning? That means because this agent never found itself in that state before, its reward structure in the inverse reinforcement learning case would not simply be able to model how to reason about this state. So this could be disastrous for certain operations where, hey, the ship was in this part of the ocean, we've never seen it before, our model doesn't know how to reason about it, right? So what we wanted to do is make our methods robust to this. So there's a series of techniques we're considering and also some novel formulation to make sure that, hey, if an agent is in a situation it's never seen before, such as these ships or in this case this robotic control task, can we allow it to reason about it based off of some of the prior observations that are not exactly the situations it's in, but very, very similar. Okay, and so this is really important for this robustness or these models to be trustworthy in actual DoD operations. So I think I'm just going to sort of wrap up with a couple things here. I think in the next year, what we kind of want to focus on is establishing that large-scale demonstration on that US Coast Guard data. I think it's a really good opportunity for people to take a look at what we're doing here. We want to actually see if we can publicly release all the code. It's based off of an academic paper. We think that would be a great tool for the community to sort of build upon the momentum of this work. Again, we want to sort of work on this novel, robust IRL problem. But also, I think the most important thing, and I think this is sort of the reason why I'm really glad to be here, is that what we want to do is collaborate with you guys on your problems. So notice we talked about things from robotic control to modeling human behavior to modeling ships. This formalism provides a large, is broad enough to be applied to a lot of different problems. And so what I really want to do is sort of pique your guys' interest in saying, hey, I have a problem that is modeling sequential behavior. Maybe this is a class of techniques that I can use. So I'm really interested in hearing what you guys have to say. I'm going to stop just so I can, if anybody had any questions about, hey, is my problem an IRL problem? Does this make any sense for me? I'd love to hear your feedback. I'll also be here later for you guys to talk to. So with that, I think I'll just close. Thank you.
Yeah, Steve Pierce, I have a question. So you're doing all this during peacetime with data that's taken peacetime.
Yep.
How robust is this technique going to be when all of a sudden we go into hostile operations and all of a sudden that ship starts moving erratically, completely different than it has over peacetime?
Yeah, so I think it's a really important question. In general for these techniques is that what happens when the data change? So the technique specifically would say, hey, something has changed. And so if we have a model in peacetime and it shifts to some sort of conflict, what we could do is then detect that something very specific is happening, not just sort of in a broad sense, but these particular actions are something that's happened. Now, as you gather more data during whatever issue is happening, then you can retrain your model to actually adjust to what's going on there, as what should be normal behavior during these conflicts. I think these models are entirely built off of the data you collect. So while I don't think you would instantly go, this model in peacetime will work in wartime, right? I think that you can identify the shift and correct your model accordingly, right? I think it's going to require some data collection on the wartime side. Any questions? Anybody have any interesting sequential behavior problems? I'm sure you do. Okay, thank you.